math and beats, it's time to talk about geometric sequences. Let's take a look at what these things are. All right, what's a geometric sequence? Well, it's obviously a sequence, and it has the form right here, a r to the k, and we're going to start our index k from 0 and go to infinity. So if k is 0, we get a. If k is 1, we get a times r. If k is 2, we get a times r squared, and so on and so on. So we also are assuming that a and r are some real numbers here, and the value of a is not 0. So, because if it was 0, then everything would just be 0. We don't really care about that. Notice also that each term in the sequence is found by multiplying the previous term by r, right? So if I take the first term a and I multiply by r, I get the second term ar. If I take the second term ar and I multiply it by r, I get ar squared, and so on and so on. Might remind you of another function you've seen before. And because of that, we can define the sequence recursively if we chose to do. It's not always that convenient, but we could do it just because we can. And that is by saying that the next term in the sequence is always found by multiplying the previous term by r, like we just talked about, assuming that a naught is a, where k here, of course, is still starting at 0. So notice k is 0. We already know we got a here, right? And so it follows that a1, plugging in k is 0 into a, so k plus 1, is r times a naught, which is r times a, or ar if you prefer, like we saw above. K is 1, plug it in, you get that a2 is the same as r times a1, which we just found. a1 was ar, so this is r times ar, which is ar squared, and so on and so on, right? So it generates the same sequence. So it's just multiple ways of representing it, but most of the time we're going to look at the explicit form like we saw originally above. So that's what geometric sequence is. We got to explore this. What does it converge? That kind of thing. That value of r, that number that each next term you get by multiplying by, we call that the ratio of the sequence. Let's look at a couple geometric sequences just to get a feel of it. So here you have 1/2 to the k. So this 1/2 to the k here is of the form ar to the k, and we're starting k as 0. So, if you just list out the terms, notice that first of all, a would be 1 and r would be 1/2. Hence, 1 times 1/2 quantity to the k is just 1/2 to the k. That's the form we're looking at. Let's write out a few terms here. So if k is 0, we get 1. There's our a value like we already wrote down. K is 1, we get 1/2. If k is 2, we get 1/2 squared, which is 1/4. If k is 3, get 1/2 cubed, which is 1/8. And then a 16th, 32nd, so on and so on. If we took the limit as k went to infinity of 1/2 to the k, that explicit formula for the terms in the sequence, that, just by understanding what we already know, and notice is just exponential really, that's just 0. So the sequence converges here to 0. So that's nice. Another example of this real quick, 4/3 to the k. All right, so this next example, we got the sequence 4/3 quantity to the k. In this case, it would tell us that a is 1 and r is 4/3, right? So therefore, ar to the k is going to be 1 times 4/3 to the k. That's exactly what we got, 4/3 to the k. Just writing out a few terms here. If k is 0, we get 1. That's our a value like we already said. If k is 1, we get 4/3. If k is 2, we're going to get 16/9. If k is 3, we're going to get 64 over 27, and so on and so on. Notice that similar to the way the exponential functions behave, this thing's just going to keep growing bigger and bigger and bigger as k gets larger. So this thing actually going to go to infinity, and hence it diverges. Okay. So what we'd like to do now is generalize what the limit of a geometric sequence is. We just saw one that converged, and notice that 1/2 there, that was a number smaller than 1. So when you keep raising it to powers of k that get larger and larger, that thing gets smaller and smaller. Here, in this second example, the base 4/3 in that sequential formula is bigger than 1. And as k gets larger, that gets bigger and bigger and bigger. So what is the limit in general? That's what we'd like to generalize. Let's let r, little r that is, be a real number. Then, here's our claim. We're going to explain this right here. If you take the limit as k goes to infinity of r to the k, right? So all different values of r. If the magnitude of r is less than 1, right here. So maybe it's 1/2, like in the example we saw. Maybe it's 1/10, like the example we saw. Maybe it's 0. Maybe it's -1/5, right? Magnitude less than 1. All values of r between -1 and 1 and not including those. That limit is 0 because that base just gets smaller and smaller and smaller in magnitude, closer and closer to 0 as k gets very, very large. If, however, the magnitude of r equals 1, then the limit is 1, because then what would you have? You would have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 forever. It's always 1. Converges to 1. Now, otherwise, if the value of r is less than or equal to -1, so -5, -20, whatever, then that's a base that has magnitude bigger than 1, and it's going to diverge for those values. But what if r was equal to -1, right? You might think, what happens there? Because that's kind of a peculiar one. Well, if r is just -1 and we consider the sequence r to the k, then that's just -1 to the k as a sequence. K is 0, you get 1, then -1, then 1, -1, 1, -1, so on and so on. Just goes back and forth between 1 and -1, so it never actually converges to a real number, and hence that limit does not exist. But if the magnitude in general is larger than 1, which is the same as saying that r is larger than 1 or that r is less than -1, then that quantity is just going to blow up to infinity or negative infinity depending on what's going on, and it's not going to converge to a real number. So the two examples prior to this were supposed to get us thinking about why this might be true and the different types of limits that can happen. So that's it. That's how we generalize the limit of a geometric sequence. And hence the end of the video. Geometric sequences, that's just a little introduction. Of course, ends up that geometric sequences are really important. That's why we're talking about them. But it might not be apparent yet, but you'll see. Okay then, bye-bye. Stay tuned for more beats and more math videos.